this thing on? Yep, awesome. G'day everyone. Welcome to Summit. Hopefully you all enjoyed the keynote. My name is Kelvin Yap. I am a product marketing manager at Atlassian. Quick show of hands. Hands up if this is your first Summit. Holy crap, okay. And hands up if been to more than one Summit. Awesome, awesome, cool. So there's obviously a pretty diverse range of experience here at Summit. This personally for me is my 5th Summit, my 4th as an Atlassian. And as much as the fellow people in the room that you'll meet over the course of the next couple of days and at Bash tonight are great, and obviously Bash itself is kind of cool. Hangovers aren't that great though in the morning. The most exciting thing, I think, are these sessions. I think these sessions for attendees are really good because you get to see how a lot of other teams and organizations are, and particularly for this track, the build and deploy, how they're doing software development, which is great. And so with software development, or I should say with this build and deploy track, over the next 2 days, it's not necessarily going to be just in this room, but in various rooms, so make sure you check your agenda. We're going to be covering all aspects of the software development process, from the process itself, the technologies used, and all kinds of great things like that. So we've got things such as, obviously today, Git large file storage, talking about continuous delivery in the cloud with Bitbucket pipelines, scaling with Docker, and all kinds of good things like that. So without further ado, I'm not going to take up these gentlemen's valuable time up on stage. I'd like to introduce Lars Schneider from Autodesk and Steve Smith from Atlassian. Lars, when he is not kiteboarding in exotic locations like the Canary Islands, is actually a contributor to the open source Git and Git large file storage projects. So he's a great person to be up on stage to talk about Git LFS. Steve is one of a handful of Atlassians that has been in the company for more than 10 years. He tells me he's got 3 passports, has lived in 3 countries in the world, but for some reason he still calls England home. It must be the aversion to the sun or something like that, I'm not sure. So without further ado, please welcome Steve Smith and Lars Schneider.
Thanks, mate. Hey, everyone. No, actually, the reason I call England home is because of its robust currency and stable government. Hey, so tracking huge files with Git LFS. How many people here know what Git LFS is? Okay, so quite a few. So we're going to dive in pretty quickly here. This is a joint one between me and Lars. Lars is very much the star of the show here. I'm just his fire-up man. So we're going to explain a bit about why Git LFS is necessary, but to do that we need to dive into a bit about how Git works under the hood. It'll be very much a high-speed, deep dive, but hopefully it'll give you enough information to talk about why big files are a problem, and a bit of an introduction to the Git LFS model, how it modifies slightly the Git model or builds upon it in order to solve this issue that is a problem for real companies, in particular for companies like Autodesk. At that point, I'll hand over to Lars, who will give you a bit more real-world experience. It's nice to talk about theory, but practical stories are far more use in my experience. And he's got some really interesting stories and practical tips and tricks about Git LFS migration for you. So without further ado, we're going to talk about the Git Data Model. This is going to be a very fast deep dive. I do a longer talk. It's available on YouTube that calls Knowledge is Power, that explains a bit more about the Git Data Model if you are interested in this. So this is very much the abridged version of that. But hopefully everyone here has got enough experience to follow with this. So to start right at the bottom, I like to tinker around underneath things. I like to know how things work. So let's start with very simple, low-level look at Git. So we're going to do a Git init right at the start. We're going to create an empty Git repository. And I'm going to poke around at it. We're going to use a command called tree here. It's available on Mac and Linux. That just gives you a little recursive view through the file system. I'm just picking on one part of it, .git objects, because that's where the main action takes place from our point of view. And as you can see, there are 2 empty directories here and not an awful lot else. So let's put something in there. We're going to use touch. It's a Unix file command. Creates an empty file or updates a file timestamp. So here we're creating an empty file. And then we're going to tell Git to track it. Git does not track anything for us by default, so we need to add it, as I'm sure you all know. So what happens? Well, this happens. A file appears, but it is not called new file or whatever. It is a hash. What happens is Git takes that content of that file. The content is important. The content is compressed with zlib, and it's got a little header is stuck on the end, and then we SHA-1 hash it. That's important. From that point on, Git only refers to the hash. And if that file changes in any way, obviously the hash will be different. So this is why we talk about content addressable file systems. So this is very important. Every time a file changes, Git creates a new version of it. And everything really in Git is built upon that abstraction, the idea that there is hashes of content, and we operate on the hashes. And if the content changes, a new hash emerges. At a slightly higher level, we start to build on new layers on top of Git, one of which is references. References are a little bit like variable names in Java or any programming language. They point at hashes and give them symbolic names. In this case, we have one called master, and that points at a commit. So we're going to have a look at this this reference called master. It is just literally a text file with that hash in it. That is why creating branches and tags and so on is so fast in Git. All we're doing is chucking a handful of bytes into a file. That's all. And if we look at the commits all point to each other. In fact, commits point back in time. Each one has a parent. So this is what's called a directed acyclic graph. This is what you hear about quite a lot. It only goes in one direction. It does not have any loops in it, but it tracks backwards through time, or at least change. Now we have a closer look at these commits. Commits are not themselves the changes. They merely track changes or state of your directory, your repository over time. So we could use this cat file command, nice low-level poking around tool, and say, show me the contents of this commit. And what it looks like is pretty much what you would expect it to look like. It's pretty much just a text file with a certain format. We have the parent, so this is why it points backwards. Important fact, if you modify the parent, you modify the hash, therefore you modify the commit. So each commit has its history essentially encoded into it, which gives you some of the security advantages of Git as well. You can't modify things without altering the hashes, which would break your tree. We also have a lot of other metadata that's fairly obvious, committers, authors, and of course your commit message. But we have one other thing here, the tree. The tree is yet another special type of object in Git. Let's have a look at that. This is where things get kind of interesting, because the commits themselves don't contain the content. The content is just pointed to. It's all just pointers pointing at things. So let's have a look at this tree file, or tree object. Now this looks like an awful lot like the entry for a Unix file system, which is a big surprise given it was written by a Unix file system guy, Linus Torvalds. So what you have here is the sort of metadata you would expect on a normal tree. In particular, you have file mode, is it executable, is it readable, writable, etc. The type of object that it is, blobs, which are just literally files, or contents that can be files, and trees. And it points to the hash. That points where the content is. And only here do we assign names. So the same content can have multiple names. So this is kind of interesting. So what happens as we build up and we start to add things? We have trees that point to other trees that point to objects eventually, and that's fine. And as we go along, these change. So we will often modify files, modify trees, add new files, remove them, etc. But because it's a content addressable file system, that empty file I created at the start, that is the name of an empty file in the known universe where the maths law applies. It's always going to be the same. An empty file in Git will always have the same hash. And that's important because that means we can reuse files. So instead of actually having copies of content all the time, every commit, every change will reuse any files that have not changed in the previous version. So it's important. These things change over time. But what happens when we're talking about large files, where it gets interesting? And more importantly, large files that change a lot. So let's have a look at one of our designers has added a baby elephant into the Git repository. That's fine, 50 meg, not that big. We've all got SSDs and they're insane sizes now anyway. So it doesn't really matter that much. But she's thinking, okay, that's nice, but the elephant's been out drinking. Let's make it a pink elephant. Now, if you're dealing with something like a GIF format file that's palette-oriented, that could be a single bit. But because the bit has changed, the hash has changed, it's a different object on disk. These are starting to accumulate now. We no longer have 50 meg, we have 100 meg, even though we only changed a single bit. And so on and so forth. As we add more and more changes, however small, we are multiplying these files. Now, again, that's not super important. It slows you down a little bit, but not much. We've all got SSDs, we've all got huge disk space, not a big problem. But the problem is we're not interested in people working by themselves. We're interested in people working collaboratively in teams. So this is where things get a bit of an issue. Because every time somebody does a pull off this repository now, they'll be getting every revision of that file every time, whether they want it or not. And that's where things become an issue. And that's where Git LFS comes in. Git LFS slightly modifies Git's semantics around certain files. You control it though, and it hooks into existing Git using the existing hook points that we already have inside Git. But it changes the model slightly when you tell it to address certain files differently. It does pretty much what you would expect it to do if you think about it. Rather than storing the files themselves, if we say certain files, these baby elephant files, should be treated differently. They're going to be large and they're going to build up. Why don't we store a pointer instead that addresses where the real content is, but only store these very small pointer files? Then when we do a push, two things happen. We push off the binary files, these large files, off to a special storage. There can be different types of storage. We're now essentially becoming pluggable at the back end. But the point is that it's stored differently and stored somewhere else. But all of the pointers go into the repository. Therefore, when you go to do a pull later, all those pointers will come out. That's fine. They're only tiny. They're a handful of bytes. But we only pull the binary content that we want. In particular, we only pull the latest version by default. We don't pull all the previous versions. Now, that is optional. There are a number of settings inside Git LFS to modify that. And you can always check out a specific revision if you so wish. And Git will go off and do the right thing for you and find that file and pull it down for you. So what does this look like? Again, always love to have a poke around underneath. There's quite a lot to poke around in here as well. What does one of these pointer files looks like? Well, it looks like exactly what you think it would look like. There is only 3 entries to this. It contains a version so that we have some backwards and forwards compatibility in the future. We store a hash. That is just a hash to the object, uncompressed, very straightforward. And we store the file size for just housekeeping purposes. So, but how does that work then? How does that work in practice? Well, the way it works is there's existing hooks inside Git called smudge and clean filters. So when our graphic designer adds this new video she's created, an MP4 of a dancing elephant for the sake of argument, what happens is Git invokes, at our request, a clean filter. Clean filters have been around for some time. And what they do is they allow you to modify or sort out content before it goes into the Git index. So at that point, we shunt the binary file off to a separate subdirectory under our .git repository, .git LFS objects, and instead place the pointer file there. We take the hash and we generate the pointer file. And that gets pushed up to our Git repository, or to our local one. What happens at the upper end? Well, when we do a Git pull or a checkout or whatever to get a new version, we receive the pointer file, and then at that point, the smudge filter kicks in. Smudge is the literal opposite of the clean filter. It takes something out of Git and says, well, I want to run some pre-processing before we put it onto disk. Obviously, that gives us the chance to see if we've got that file locally. If we do, we just use it, we just swap it in. Or if it's not there, we go off to the remote repository and find it from there. Only then do we replace the binary file with the pointer file on disk. So one of the key points here is we store pointers in the objects and in the main repository, and we store the binaries on the local file system in a separate directory or inside the cloud. It's actually very easy to set up, just for a real practical issue. You can just install Git LFS, and it just works once it's in your path. And once, and only once per user, you have to do a Git LFS install, because that does a little trick where it modifies the core Git config, your user-wide Git config, and adds this filter in that says, when I'm dealing with LFS files, we invoke the smudge and clean filter at certain key points. That's all very well. How do we tell it which files are LFS? Well, that's on a per repository basis. We just say, track all MP4 files as Git LFS, and all it does is modify your local Git attributes. And that says, when you're dealing with files called MP4, invoke the clean and smudge filters on my behalf. And you do that on a per repository basis. Now, this is all very well, and just gives you the basics of you have now enough to work with Git LFS on a day-to-day basis on your working tree. However, there's a little bit more to it than that. And of course, when you're dealing with collaborative workflows, you need to think about how people are going to interact together and questions of migration. The best person to talk to you about this is Lars Schneider. Lars, as Kelvin said, is a contributor to both Git LFS and Git Core, and works for Autodesk, where he's a technical lead in charge of managing Git and Git LFS migrations across a massive company that I think should need no introduction. Autodesk deal with massive files and massive content all the time, and he's here to talk to you a bit about the practicalities of running a Git LFS arrangement. Thank you, Lars.
Thank you. Thank you, Steve. Yeah, as Steve said, my name is Lars Schneider, and I'm the technical lead for Git at Autodesk. That means I'm concerned with all things around Git at Autodesk. So I make sure our engineers use the right Git workflows, and if our engineers run into any issues, then I address them. Sometimes I address them in the source code, and these patches I usually contribute back to the Git and Git LFS community. But first of all, who are we? Who is Autodesk? Autodesk is best known for AutoCAD. That's a 2D and 3D computer-aided design software. We are in business for more than 33 years, and we have more than 4,000 engineers working on hundreds of products that consists of terabytes of code and asset data. We have products in the architecture, engineering, and construction space. So if you see a building or a bridge, it's likely that Autodesk software was involved. We have products in the manufacturing space. So the airplane that you have arrived with probably had parts that were manufactured using Autodesk software. We have products in the media and entertainment space. So if you've seen a movie like Avatar or a series like Game of Thrones, then you've already seen the results of Autodesk software. And more recently, we have products in the 3D printing space. We call this the future of making things. So what do we use Git LFS for at Autodesk? Mostly, we use it for integration test data. In our case, these are usually 3D models. But we also use it for auxiliary data. That means for documentation, for images, for videos. We use it for pretty much everything that is closely related to the source code, but that does not have an own version identifier. Some teams at Autodesk, they even use it for build artifacts, but we usually don't recommend that because we have specialized services, such as Artifactory, for these kind of use cases. So we use Git LFS for almost a year now, and we have learned a number of things. And I want to share these learnings from the perspective of 3 different personas. First, from a perspective of a migrator. That is someone who migrates source code to Git with the help of Git LFS. Second, from the perspective of the developer. And third, from the perspective of the repository administrator. So let's start with the migrator right away. So over the last year, we migrated a lot of projects to Git with the help of Git LFS. And we usually followed this kind of process. First, we've identified an engineer with deep code knowledge of the project that we want to migrate. And we talked to this engineer. So we figure out what part of the repository is really source code and should go to Git, what parts are assets and should go to Git LFS, and what parts of the source code is third-party code that should actually go somewhere completely else, like Artifactory, and what part of the source code shouldn't be in the repository at all. And after we know that, we create a so-called demo migration on a special Git migration server. And then the engineer takes this demo migration and tries to build the product and tries to set up the CI and so on and so forth. And usually we encounter some problems. So it takes a couple of iterations until the repository is in a good state. And when we have this repository in a good state, then we ask the broader team to play with this repository. That means we ask them to clone the repository, to create branches, to create commits, to work with the repository. Why is this necessary? Well, you have to keep in mind, most of our engineers haven't used Git or Git LFS before. So this is very, very valuable feedback for us. And we can ensure that there are no problems with the repository and that the people could run into. And as soon as the team gives us a go that everything works well for them, we perform the actual production migration on our Git production server. So how does such a migration look like? As I said earlier, Autodesk is around for more than 33 years. And for historical reasons, our source code has been in all kinds of different version control systems. We had products in Subversion, in TFS, in Perforce, and we even have some products that use their own version control system. And as a first step, we usually use open source tools such as Git SVN, Git P4, or Git TVS to migrate these repositories to Git. And then we have a bunch of scripts that analyze the Git repositories. We make sure we don't have third-party code in there, and we have scripts that identify possible candidates for LFS. And then in a second step, we use the Git filter branch technique or an open source Java tool called Git LFS migrate to separate Git and the Git LFS files. The great majority of our migrations actually happen from Perforce to Git, and we use Git P4 for that. In order to speed up these migrations, we added native LFS support to Git P4. These patches have been accepted by the Git community and are available since Git 2.7. So some of these projects that we've migrated have a long, long history, more than 20 years, easily. And something we noticed is that if we migrate these big projects as is with all the history to Git and Git LFS, then we will require a lot of space on our LFS storage system. And then we ask ourselves, is this necessary? So for source code, of course it is necessary to have all history, because the engineers, they want to know where every line came from. But for binary files that have been deleted like 5 years ago, engineers usually don't care about them anymore. So what we did is we just discarded them from the migration. And that made our migrations faster, and we used less space on our LFS storage system. So that's a good thing for us. And there was something interesting that we've noticed when we rewrote the history of these Git repositories with lots of LFS files. It turns out when you remove an LFS pointer from the history of a Git repository, that does not mean, so when you remove the pointer, the content that the pointer points to in the LFS storage system is still occupied. And this is actually by design, because Git LFS is designed in the same way as Git. That means whatever you add to Git LFS will stay there. So please be aware of this fact. And how we deal with it? Well, that's actually the reason why we perform our migrations on a special migration server first, because you create these kind of orphaned LFS files during the migrations process way more often than in a production environment. All right, next I want to talk about the perspective of the developer. And with developer, I also mean designer, tester, pretty much everyone who is working with the Git LFS repository. And I think the most important thing is that you teach your developers why large files are a problem in Git. And Steve just gave us a very detailed explanation why that is the case. But the gist of it is really because Git is a distributed version control system. And that means all history is local. That is very good for source code files, but that can be a problem for large files, especially if you have the large files with all the history on your local machine. And Git LFS can solve this problem very nicely. So when I introduce Git LFS to teams, pretty much the first question that I get is, what is a large file? At what point is the file too large for Git? And it turns out that the size is actually not the right metric to look at. So what files are not suited for Git? It turns out that files that do not compress well are not suited for Git, because Git is optimized for source code files and not for binary files that don't compress well. A good example for a file that does not compress well is a video file, because video files are usually compressed pretty heavy already, and Git can't compress that further. So when you add a 10 megabyte video file to your repository, then your repository will grow by 10 megabyte. And then you might say, well, 10 megabyte, that's not a big deal. Especially today, we have such a high bandwidth, nobody will notice. That's true. But think about it. Let's say this 10 megabyte file is actively worked on, and your designer changes this file every day. So you add 10 megabyte to your repository every day. After a year, your repository size will grow to a size of around 3 gigabyte. And this will actually be a problem, because if you clone a repository with the size of 3 gigabyte, this is something you will certainly know or realize. So to summarize that, what files are not suited for Git? Files that do not compress well and change frequently. So this is the detailed answer, but as a rule of thumb, we tell our engineers files that are smaller than 500 kilobyte are usually okay for Git, even in the long run. If you have larger files, then you need to find other solutions, such as Git LFS. All right, Steve just told us how you track files with Git LFS. You use the Git LFS track command, which is great and usually works pretty good. But there are a few edge cases that I want to talk about. Let's say you add a couple of large PNG files to your repository, and you think, well, okay, they are maybe 50 megabytes, so I should use LFS for it. And then you use the LFS track command with star.png. So after you've done that, you realize your Git repository got really slow. All kinds of Git operations are super slow. So what happened? It turns out you have these very big PNG files, but you also have a couple of thousand icons in your repository that are also PNG. And when you use this pattern, star.png, then all of these files are under LFS control. And LFS has a certain overhead that makes Git operations slower. So what can you do about that? Well, one thing is you could use creative tracking patterns. Instead of tracking the extension of the files, you could track a special string in the name of the files. For instance, .lfs. And then you name your large files according to this pattern, and then you can track them individually. Another approach is to create a special directory for large files, and then you track all the files in this directory, like this. A third option is to track large files individually. That works great, but you need to be careful when you rename or move these kind of files, because then you need to adjust the tracking patterns too, because otherwise the file would be added to Git, and it's something you don't want. In general, we tell our engineers less than 1,000 files are okay in Git. You won't notice any speed problems at all. This rule works for a number of projects at Autodesk, but we have also a number of projects where we have way, way more than 1,000 files that are large. So this was a very big problem for us, and that's why I'm working for the last couple of weeks with the Git and the Git LFS community to implement a new protocol between Git and Git LFS that makes the communication faster. And the first tests are looking very, very good. So it's all about a speed improvement of almost 2 orders of magnitude. And the Git core guys are still reviewing the code. And I really hope they will accept it soon. That would be very useful for our LFS usage. But if you have to work with repositories that have a great number of LFS files today, then you could use a trick. And that trick would be to use Git sparse checkout. With sparse checkout, you can define what LFS files you're actually interested in, and then Git would only process those, which then would make your repository really responsive again. All right, and now I have a few tips and tricks around Git LFS usage in general. So first, a gotcha. When you use the Git LFS track command, then please be aware that this tracking is case sensitive. You wouldn't notice that on Windows or Mac, because Windows and Mac, they have usually by default case insensitive file systems. But if a Linux developer joins your team, then you can run into trouble. So what can you do about this? You can use glob patterns with the LFS track command to track certain strings case insensitive, as you can see here. As we talk about gotchas, there's one more, and that is that Git does not perform line ending conversions on LFS files. So let's say you decide to add a very, very, very large text file to your repository using Git LFS, and you add that file on the Mac, then it looks like this. You have proper line endings. And if your Windows developer looks at the file, then the line endings will be broken. So please be aware of this gotcha. Another trick or tip is set up your Git credential helper, because Git LFS needs to authenticate against the LFS storage server. And it uses the same credentials that you use to authenticate against the Git server. And you really don't want your engineers to enter the credentials multiple times. That's super annoying. So use the credential helper. Next thing, use Git LFS clone to clone repositories, because this command is around 10 times faster than an ordinary Git clone command. This is a little trick that Steve Streeting and I worked on, and it works really, really good. There's one other thing to know in that area, and that is if you have a repository that has submodules that contain LFS files, then you really want to make sure that you use at least Git 2.9, because I added a little patch to Git 2.9 that makes this Git LFS clone speed improvement work for submodules too. In general, you should always use the latest Git and Git LFS version, because both projects are under active development, and you get new features and speed improvements pretty much with every version. All right. Last but not least, I want to talk about the perspective on LFS from the administrator point of view. As an administrator, it's very important that you ensure that Git LFS is installed on all platforms. And that's a pretty hard task at Autodesk, because we have a variety of different operating systems that we use and different configurations. But this is very important, because otherwise an engineer would clone a repository, and if Git LFS is not configured correctly, then they would see these Git LFS pointer files, which are very confusing. So what did we do? We came up with enterprise config for Git. That is a tool on top of Git config that configures a local Git installation. And it does a number of things, and amongst these things is it installs the right version of Git LFS and configures it correctly on all kinds of operating systems. And it's open source. You can look at it and configure it for your own usage too. It works great at Autodesk. We have lots of users. But even if you make sure that Git LFS is properly installed on your developers' machines, that does not make sure that your engineers will use it in the right way, right? So, and your engineers can still add large files to their Git repository. And as you all know, whatever you add to a Git repository will stay there forever. Okay, some of you will now say, well, you're not right. You could use the git rebase command to change the history and remove these large files from the history again. Of course you could do that. But if you have a team of 100 people working with a Git repository, then you get in a lot of trouble when you perform this rebase command. So you should try to avoid that as much as possible. And how could you do that? Well, one very effective way is to reject pushes to your Git server that contain large files. That works great for us. However, there's a little catch, and that is, if someone pushes a commit with a large file, then the commit was already made. And the only thing that the server would tell you is, well, I don't accept your commit, you need to change that. And you could change that with the rebase command, of course, but for a Git starter, and we have lots of them at Autodesk, using rebase might be complicated. So that's a problem. What can we do about this? Well, you could try to make sure that the commit is not made in the first place. And you can do this with a Git pre-commit hook that is running locally on the developer's machine. And we are experimenting with this right now. And as soon as we have a solution we are really happy with, we will push that to the enterprise config for Git repository. So these automated solutions to ensure that large files are not added to your Git repository, they are great. They are great to make sure that you don't, accidentally add a large file or something. But in the end, it's a machine that tells you, I don't accept your work. And that can be frustrating to engineers, and especially to engineers that just moved to Git and Git LFS and where everything is new and they don't really know their ways around it yet. That's why we use a different strategy for large teams that we move to Git and Git LFS. And that is, we review their work, their Git LFS usage. So how do we do that? In a large team, a developer works on a feature, has a branch, works on a feature, uploads the branch, creates a pull request, and then the pull request is reviewed by someone with domain expertise. And after this review is done, the reviewer will notify a Git experts team. And then the Git experts team will quickly look over the pull request and will make sure everything is sound from a Git and Git LFS perspective. And then this Git expert gives the go for the final merge. This worked really well for us because if there's something wrong, then the original developer has a human person to talk to that can explain what went wrong and how the problem can be fixed. And this way, the developer crowd will learn really quickly how to use Git and Git LFS properly. And yeah, we did that after some migrations for the first couple of weeks and had very good results. All right, so to wrap that up, first and foremost, the most important point here is Git LFS works at scale. It's actually the main reason why Git works at Autodesk at all. Second point, you really should make sure that you automate your Git LFS setup. This way, your developers will never see these pointer files, and Git LFS will just work for them. Third, make sure you use the fast clone command because it's way faster than the regular clone. Fourth, use smart tracking patterns, at least right now, because Git LFS gets slow after 1,000 files are added to Git LFS. And last but not least, reject large files in Git and try to reject them early on. So that's it. And now I would like to open the discussion and answer your questions. Thank you.
Awesome. Thanks, guys. That was great. I forgot to mention one thing, and that was if you haven't downloaded the app, please download the app. Second of all, you can ask questions or submit questions during the session itself through the actual agenda too. And through the app, you'll be able to submit or provide some feedback on what you thought about the session. That'd be great if you could do that too. We've got a couple of minutes. I know it's lunchtime, so I don't want to kind of eat away, pun intended, at your lunch break. Does anyone have any questions? I'm happy to run over and ask them. Yep, we've got two over there. One sec.
Hey, it's a good talk, by the way. I had two questions. One, can you go into more detail on how you migrated those old repositories and pulled those large binary files out? And is it possible for the LFS filter to check, say, is it a PNG file and it's above, a megabyte or something like that, so that you don't have to do the check on the server and refuse the push?
Okay. I will start with the second question first. So, is it possible to make a decision based on the size? Unfortunately, it is with the default Git. It is not, because the Git clean and smudge filter, they were not intended for this kind of use, and so the size is no criteria to invoke the filter or not. And actually, I'm thinking on that topic for quite some time now, how we could get that into the Git core mechanism. The only way that you could really look at the size and then decide if you want to use LFS or not is really with pre-commit hooks, as I said earlier. But if you use pre-commit hooks, then you would need to track these files individually. So if a file is large, then you track it with the entire path. If it's not large, then you just don't track it. But if you use like these wildcard patterns, then size is no criteria right now. But I know a number of people in the Git community are working on this, and maybe someone can come up with a good strategy how we could make size a criteria for these kind of files. The problem is really that there are two communities, the Git community and the Git LFS community, and you need to find, and we need to, you need to please both. That's a little bit harder than you might think. Okay, then to address the first question, how do we ensure that certain files don't go into the migration? We try to use mechanisms of the source version control systems where the source code was stored before. So for instance, in the case of Perforce, we used a special client spec to remove files from the history. So we just ignore them on the migration. That's one strategy. And the second is we ignore. As I said earlier, we used the Git P4 tool to migrate stuff from Perforce to Git, and I have a patch that is not yet contributed back, but I'm working on it. And this patch looks at binary files, and if the binary files are older than a certain date, then they will just not migrate them. It will just migrate an empty file. So these kind of tricks we use. But they are really, I can't give you a general answer for that because this really depends on the version control system that you use. And yeah.
There is an additional case there. I don't know if you were talking about if you have an existing Git repository that already has large files in it, and you want to migrate that to a Git LFS one. There are a couple of solutions to that. One is that you can use filter branch. It's a really, really complex. Go look it up. It's an incredible piece of work. Complex filter branch that runs through and basically uncommits and recommits all the files as Git LFS. But there are two other tools. One's called it's BFG. It's a tool built in Scala on top of the JGit, designed to be much faster, and it's designed for killing history, but it now explicitly supports Git LFS as of some recent versions. There's a new tool called Git
LFS Migrate.
Migrate, which is custom built just for migrating Git LFS. So there are tools out there to help you rewrite history. Of course, you're going to have to archive your old version and then push up a new version because your entire history will have changed effectively. But if you do need that kind of solution, then there are tools out there. I do have an additional talk that's kind of complementary to this one, myself and originally by Tim Peterson from Atlassian, that talks a bit about this. It's up on YouTube called, I think, Git LFS, and it discusses some of the trade-offs of the various solutions for migration of existing Git repositories.
Cool.
Yeah, you really should get familiar with the Git filter branch command. It's, as Steve said, super powerful, and it can do much, much more than all the other tools. The problem with it is that it's really slow. If you have a repository with lots and lots of history, then it can take a long, long time on a heavy machine to process all the commits.
Awesome. Run out of time. Sorry, maybe you could catch up with Lars and Steve to ask you a question at the end. Quick reminder, if you could please answer or provide some feedback on the app for Lars and Steve, we'd much appreciate it. But lunchtime is on right now. Next session starts at 1:30, but in the meantime, enjoy. Thank you very much for attending.